Every year, mining companies move 3 billion tons of earth to extract just 3,000 tons of gold. That's roughly 1 million tons of rock for every single ounce of the precious metal sitting in your jewelry box. This staggering ratio reveals the true scale of modern gold mining, an industry that generates over $400 billion annually, while employing more than 4 million people across 6 continents. South Africa alone processes 800 million tons of ore each year, while operations in Nevada move enough material daily to fill the Empire State Building twice over. Yet despite this massive industrial footprint, most people have never seen how raw rock becomes the gleaming metal that backs currencies, fills dental crowns, and enables the smartphone in your pocket to function. The transformation begins in open-pit mines that stretch for miles across landscapes, where the first challenge is identifying which rocks actually contain gold. Massive haul trucks, each weighing 400 tons when loaded, transport ore from blast sites to primary crushers that can process up to 8,000 tons per hour. These crushers, some standing 6 stories tall, use rotating steel jaws to reduce house-sized boulders into fragments no larger than basketballs. The sound is thunderous, a constant grinding that can be heard from miles away, while dust clouds rise hundreds of feet into the air, despite water spraying systems working continuously to suppress them. At this stage, the ore contains as little as 0.5 grams of gold per ton. Imagine finding a single paper clip in a small car full of gravel. Yet even at these microscopic concentrations, the economics work because of the sheer volume processed. A single large mine might crush 50,000 tons of ore daily, yielding just 25 kilograms of gold. But at current prices, that's worth over $1 million per day. The crushed ore moves to ball mills, rotating steel cylinders the size of subway cars filled with steel balls weighing up to 100 pounds each. As these mills rotate, the balls cascade down, pulverizing the rock fragments into powder, fine enough that you could blow it away with your breath. The grinding process consumes enormous amounts of energy. A single large ball mill uses as much electricity as a small city, or running continuously for decades. This grinding stage is where the real precision begins. The particle size must be exactly right. Too large, and the gold remains locked inside rock crystals. Too small, and the subsequent chemical processes become inefficient. Advanced sensors monitor particle size in real time, adjusting mill speed and adding fresh grinding media as the steel balls themselves wear down and become part of the ore slurry. The powdered ore, now mixed with water to form a slurry, enters flotation cells, where chemistry takes over from brute force. Specific chemicals are added that make gold-bearing particles hydrophobic. They repel water and stick to air bubbles instead. Compressed air is pumped through the slurry, creating billions of tiny bubbles that carry the gold-rich particles to the surface as froth, while worthless rock sinks to the bottom. This process concentrates the gold content from 0.5 grams per ton to as much as 100 grams per ton, a 200-fold improvement. The froth, which looks like chocolate mousse, is skimmed off continuously and contains not just gold, but often silver, copper, and other valuable metals that make the entire operation economically viable. A single flotation circuit can process 10,000 tons of slurry per day, while using enough chemicals to fill an Olympic swimming pool weekly. Many gold ores contain sulfide minerals that lock gold inside crystal structures, making it inaccessible to chemical extraction. These concentrates enter massive roasting furnaces that reach temperatures of 1,200 degrees Fahrenheit, hot enough to melt copper. The roasting process breaks down sulfide minerals, releasing sulfur dioxide gas that's captured and converted into sulfuric acid, a valuable industrial chemical sold to other industries. The roasted ore emerges as a fine, reddish powder that's been fundamentally transformed at the molecular level. What was once locked gold is now accessible, but the process requires precise temperature control and sophisticated emission control systems. A single roaster processes 500 tons of concentrate daily, while producing enough sulfuric acid to supply a medium-sized chemical plant. The roasted ore enters the most chemically intensive phase of gold extraction, and sodium cyanide solution, heavily diluted but still requiring extreme safety protocols, is mixed with the ore in massive tanks called leach vessels. Gold dissolves into this solution through a process that occurs naturally in some environments, but is accelerated and controlled here. These leach tanks, some holding millions of gallons, operate like massive washing machines running for days at a time. The cyanide solution has an almost magical selectivity for gold, dissolving it while leaving most other metals untouched. A typical leaching circuit processes 20,000 tons of ore daily while using cyanide concentrations measured in parts per million. Deadly to humans, but carefully contained within multiple safety systems. The pregnant solution, industry terminology for cyanide solution loaded with dissolved gold, contains just a few grams of gold per 1,000 liters. Yet when multiplied across the enormous volumes processed, this represents millions of dollars worth of precious metal flowing through pipes and tanks in liquid form. Activated carbon granules, each piece smaller than a rice grain, but with internal surface area equivalent to a football field, are mixed with the pregnant solution. Gold ions have a natural affinity for carbon, adhering to its surface in a process that effectively pulls gold out of solution. This carbon in pulp process can recover over 99% of dissolved gold. Cyanide. The gold-loaded carbon is separated from the slurry and washed with hot caustic solution that strips the gold back into liquid form, creating an extremely concentrated gold solution. At this stage, what started as tons of rock has been reduced to just a few hundred liters of liquid containing several kilograms of gold, a concentration increase of millions to 1. The concentrated gold solution enters electrowinning cells, where direct electrical current causes pure gold to plate out onto steel cathodes. These cathodes, looking like metal mesh screens, gradually accumulate layers of gold that can be peeled off as thin sheets. The process consumes massive amounts of electricity. A single electrowinning circuit uses enough power to supply 1,000 homes. The gold sheets, still containing small amounts of other metals, are melted in induction furnaces that reach temperatures of 2,000 degrees Fahrenheit. Flux materials are added to bind with impurities, which float to the surface as slag and are removed. The molten gold is poured into molds, creating doré bars that are typically 90% pure gold. The final transformation occurs in specialized refineries, where doré bars are dissolved in acid solutions and subjected to additional purification processes. An electrolytic refining passes electrical current through gold-bearing solutions, depositing pure gold onto cathodes with precision that achieves 99.99% purity, a level where impurities are measured in parts per million. This ultra-pure gold emerges as cathode sheets that are melted and cast into standard bars weighing exactly 400 ounces each. These bars, worth over $800,000 at current prices, represent the end point of a process that began with millions of tons of ordinary-looking rock extracted from deep within the earth. The entire journey from raw ore to refined gold typically takes between 30 and 90 days, depending on the specific processes used and the characteristics of the ore. Modern mining operations achieve remarkable efficiency. The largest gold mines can process over 100,000 tons of ore daily, while maintaining environmental standards that would have been impossible just decades ago. Water used in processing is recycled multiple times, with some operations achieving over 90% water reuse rates. Waste rock and tailings are carefully managed in engineered facilities designed to prevent environmental contamination for centuries. Even the cyanide used in leaching is recycled and reused, with modern operations losing less than 1 kilogram of cyanide per ton of ore processed. The scale of coordination required is staggering. A single large gold mine operates like a small city, with its own power plant, water treatment facility, analytical laboratories, and transportation network. Thousands of employees work in shifts around the clock, maintaining equipment worth hundreds of millions of dollars, while processing material that arrives continuously from multiple pit locations. The next time you hold a piece of gold jewelry or use a smartphone with gold-plated circuits, consider the industrial symphony that made it possible. That tiny amount of gold represents the coordinated effort of massive machines, precise chemistry, and human expertise applied to transform ordinary rock into one of humanity's most treasured materials. Tibor, how many other everyday objects around you required similar industrial transformations that remain completely invisible to most people? If you're fascinated by the hidden industrial processes that create our modern world, subscribe to see how other raw materials undergo equally remarkable transformations on their journey to your daily life.